It's 1971. In a dimly lit lecture hall, Professor Milton Ash stands before a half-awake audience, his voice droning over a sea of bored faces. The topic, K-On Decay, a subject so technical that even the most dedicated students struggle to stay alert. Yet, as Ash absent-mindedly flips through his slides, something unusual is about to happen. This seemingly mundane moment, marked by yawns and wandering thoughts, will soon set the stage for one of the most surprising discoveries in modern physics. Sometimes, the most extraordinary revelations begin in the most ordinary settings. As Professor Ash continues his lecture, a technical mishap causes a slide to project the wrong data. The audience barely notices, but this accidental display will prove to be a turning point. Amidst the monotony, a single postdoctoral researcher, Alara Voss, sits upright, her curiosity piqued by the odd pattern on the screen. While most see only numbers and graphs, Voss senses something out of place, a subtle anomaly that hints at a deeper mystery. This fleeting moment, almost lost to boredom, is about to ignite a scientific revolution. Let's pause and set the stage. This is not just a story about physics, but about how the smallest details can lead to the biggest breakthroughs. The theme of our journey is clear. Sometimes a yawn or a stray glance can change the course of science. We're about to follow the path from a sleepy lecture hall to the edge of the known universe, exploring how a single observation can unravel the fabric of reality itself. Professor Ash's research focuses on K-On decay, a process involving subatomic particles that has puzzled physicists for years. The data is dense, the equations complex, and the implications far-reaching. Yet Ash's approach is conventional, seeking to explain an unresolved parameter within the existing framework. He overlooks the possibility that the answer might lie outside the box, in a realm no one has yet considered. The audience, lulled by the technical jargon, misses the subtle clues hidden in the numbers. While most attendees drift into daydreams, Alara Voss's attention is caught by a peculiar wiggle in the K-On decay data. It's a small, almost imperceptible deviation, but to Voss it stands out like a beacon. She wonders if this anomaly could be more than just a statistical blip. Could it hint at a hidden symmetry, a pattern that no one else has seen? Her mind races with possibilities, setting her on a path that will challenge the very foundations of physics. After the lecture, Voss lingers in the empty hall, her mind replaying the odd data. She pulls out her notebook and begins to sketch the patterns she remembers. The more she analyzes, the more convinced she becomes that the anomaly is real. It's as if the data is trying to tell her something, a message hidden in the noise. Voss decides to dig deeper, determined to uncover the truth behind the mysterious wiggle. As Voss examines the data, she notices something even more intriguing, a pattern that suggests a possible swap of coordinates. Could the particles be behaving as if their positions were mirrored? This idea, radical and untested, opens up a new avenue of thought. Voss wonders if she stumbled upon evidence of a deeper symmetry in nature, one that could rewrite the rules of physics as we know them. Still seated in the lecture hall, Voss begins to contemplate the implications of her discovery. What if particles could move not just through space but also backwards in time? The mathematics is daunting, but the possibilities are exhilarating. If true, this could mean that every event in our universe has a mirrored counterpart, unfolding in reverse. The concept is mind-bending, but Voss is determined to follow the evidence wherever it leads. Voss's realization opens up a new dimension of inquiry. If particles can be mirrored in both space and time, what does this mean for our understanding of reality? She sketches diagrams and equations, searching for patterns that might confirm her hypothesis. The more she explores, the more convinced she becomes that she's on the verge of something monumental, a discovery that could change the way we see the universe. At the heart of Voss's investigation lies the CPT Theorem, a fundamental principle in physics that asserts the combined operations of charge conjugation C, parity transformation P, and time reversal T leave the laws of physics unchanged. This theorem suggests that for every particle there could exist a mirror counterpart, behaving in a universe where charges, spatial coordinates, and time are all inverted. The implications are profound, hinting at a symmetry that underpins all of reality. Imagine a universe where every particle, every force, and every event has a mirrored counterpart. In this mirror universe, left becomes right, positive becomes negative, and time flows backward. The concept is both elegant and unsettling, challenging our deepest assumptions about the nature of reality. Voss's work suggests that this mirror universe isn't just a theoretical curiosity, it could be as real as our own. To support her hypothesis, Voss dives deep into the mathematics of particle physics. She examines equations that describe how particles behave under various transformations, searching for evidence of symmetry. The calculations are complex, but the patterns are unmistakable. Every step brings her closer to confirming the existence of a mirrored reality, hidden just beyond the reach of ordinary observation. Voss's calculations reveal a startling possibility. Every particle in our universe may have a mirror twin. These mirror particles would interact with each other in a parallel reality, governed by the same fundamental laws but with all properties reversed. The idea is both thrilling and daunting, opening up a new frontier in the search for understanding the cosmos. If mirror particles exist, the implications for physics are profound. It could explain some of the universe's deepest mysteries, from the nature of dark matter to the imbalance between matter and antimatter. Voss's work suggests that the answers to these questions might lie not in what we can see, but in what is hidden from view, a shadow universe perfectly balanced with our own. As Voss shares her findings, the scientific community reacts with a mix of skepticism and excitement. Some dismiss the idea as fanciful, while others see it as a bold step forward. Debates rage in lecture halls and conference rooms, with physicists arguing over the evidence and its implications. The controversy only fuels Voss's determination to prove her theory. To test her hypothesis, Voss and her colleagues design a series of experiments aimed at detecting mirror particles. These experiments push the limits of technology and imagination, requiring new detectors and innovative approaches. The search is painstaking, but every step brings them closer to uncovering the truth about the mirror universe. Today, the search for the mirror universe continues in laboratories around the world. Physicists use cutting-edge equipment to probe the smallest particles, looking for signs of their elusive twins. While definitive proof remains elusive, the evidence is mounting, and the dream of discovering a mirror reality is more alive than ever. The story of the mirror universe is a testament to the power of observation. Voss's breakthrough began with a single, attentive glance at a seemingly insignificant detail. It's a reminder that science advances not just through grand theories, but through careful attention to the world around us. Every observation, no matter how small, has the potential to change everything. Voss's journey underscores the importance of active engagement in the scientific process. It's not enough to passively absorb information. True discovery requires questioning, probing, and thinking beyond the obvious. The greatest breakthroughs often come from those willing to look deeper and challenge the status quo. The tale of a yawn heard around the world is more than just a quirky anecdote, it's a lesson in the unpredictability of discovery. Sometimes, the most profound insights emerge from the most unremarkable moments. By staying curious and attentive, we open ourselves to the possibility of changing the world, one observation at a time. As our story concludes, the search for the mirror universe continues. The questions raised by Voss's discovery remain at the forefront of physics, inspiring new generations of scientists to look beyond the obvious. The universe is vast and mysterious, and who knows what other secrets await those willing to pay attention? The next great discovery could be just a yawn away.